So good evening. Tonight we're going to discuss marks and channels. And marks are the basic geometric elements that depict items or links in visualizations. And channels are the things that control the appearance of those marks. So as always, Munzner begins her chapters with an overview called depict. And again, to repeat the definitions, the marks are the basic geometric elements that depict items or links within the visualization, and the channels are the things that control the appearance of those marks. And this is a good analysis framework. To quote the author, even complex visual encodings can be broken down into the components that can be analyzed in terms of their marks and their channel structure. The effectiveness of a channel for encoding data depends on its type. The channels that perceptually convey magnitude information that you see there on the left are a good match for order data, and the channels that convey identity information, which are the ones on the right of this diagram, are good for categorical data. The identity channels tell us information about what something is or where it is. In contrast, the magnitude channels tell us how much of something there is. So defining marks, again, a mark is a basic graphical element in an image, and it's the basic thing that depicts an item or a link. They're primitive objects that can be classified according to a number of spatial dimensions that they require. So a zero-dimensional point or mark is a single point that you see there on the left. One-dimensional mark is a line. A two-dimensional mark is an area, and there are also three-dimensional marks that are volumes that are possible, but those aren't frequently used. So basically, we define the marks in terms of the number of dimensions that they have. Channels are a bit more difficult, and it's a way to control the appearance of those marks independent of the dimensionality of the geometric primitive that we're using, whether it's a point, a line, an area, or a volume. You can see color, tilt, shape, size, volume all appear as different types of channels. So we can combine the marks and the channels to make our visualization. So this actually shows a progression of chart types, each one showing one more quantitative data attribute by using more visual channels. So part A, there are bar charts that show two attributes. The height of the bar conveys only one quantitative attribute, and the categorical attribute is spread along the horizontal axis there. So you would have three categories and three heights. The scatter plot uses a point as a mark for spatial position, making one quantitative attribute for position and adding hue or color. We now have a second quantitative attribute, although it's a bit difficult to see that. By adding another color, in part C, we now have three quantitative attributes, and by adding size in part D, we now have four quantitative attributes. So we can keep adding attributes by adding more channels. So there are two principles to guide the use of visual marks and channels in visual encoding. The expressiveness principle dictates that the visual encoding should express all and only the information in the data set. For example, ordered data should be shown in a way that our perceptual system intrinsically senses as ordered. Now, as a converse to that, unordered data should not be shown in a way that implies order. Identity channels are the correct match for the categorical attributes that have no intrinsic order, for example, scatter plots. And the magnitude channels are the correct match for the ordered attributes, both ordinal and quantitative. The effectiveness principle dictates the importance of the attribute should match the salience of the channel. So the most important attributes should be the ones that are the most notable. So what are the rankings of the channels? Well, here they are according to my father. TBS was his least favorite, ESPN, WWE Network, which is now defunct, and USA Network. Those are the ones that he would watch. So those aren't really the channel rankings for the channels we're talking about. Here are the channel rankings. And different channels are more expressive than others. So notice both the identity and magnitude have channels related to spatial position at the top in the most effective spot. The attributes encoded with position will dominate the user's mental model. Their internal mental representation used for thinking and reasoning compared with those that are encoded in any other visual channel. And channels have different effectivenesses. This is Stephen's Psychophysical Power Law that basically allows us to look at the effectiveness of different channels. You can see in blue, electric shock is 3.5. Saturation of color is 1.7. Length is 1, area is 0.7. So again, a little bit more difficult to discern areas. Depth 0.67, and brightness, oddly enough, 0.5. And it must have been cool doing research back in the 1960s and 70s, and there's a number of different things that we have as links in the bottom in the notes pages. But the psychophysical power law looks at the sensation, the physical intensity, and the channel exponent, which measures how effective it is. So discriminability is if you encode data using a particular visual channel, are the differences between items perceptible to the human as they are intended? Some channels have a limited number of bins, that is, limited number of things that you can put in them. For example, line width. It's difficult to tell between a multitude of different line widths. So there's limited number of line widths that can be used. You can't maybe tell 1 point thickness from 1.5 thickness, but you can tell 1 from 5. But limited number of bins, and so basically the number of bins are places where it's effective should be greater than the number of values that need to be encoded. So here, some channels are independent but can interfere with one another. The first one is fully separable, position and hue. We can separate the position of those dots along with their color. The second one has some interference. We can distinguish between large and small half, but within the small half, it's hard to distinguish between the two colors. So it's hard to distinguish between that purple and that blue, but we can certainly distinguish between the large and the small. The third example, encoding one value on the horizontal axis and another on the vertical side, is ineffective because we directly perceive the planar scale of the circles, and it's hard to basically these circles are tilted in various manners, but some of them may all be the same size. And then red and green produces major interference, and that's the most common type of color blindness there. And this one, it's really hard to separate the channel because they're not perceived separately, but it's a combined perception of color that we're experiencing when we're looking at that image over there on the right. Here's another example of marks and channels. In this transportation viz, you can see the line and hue being used as channels. So the line width and the color of the line. So the red is railroads, the blue is waterways, and the brown is the national highway system. And basically the amount that's being transported over those particular channels is shown by the line width. So you can see the Mississippi River there clearly in blue. You can see the highway system in the brownish red, and the regular red is the railways. And it's interesting why you might see things originating in Wyoming and going to Chicago. If anyone can think of what would be transported there in terms of major tonnage, let me know. I know the answer there, but it's interesting to ponder what things may be going across the US and how they're being shipped across the US. So in terms of effectiveness, another item that we might want to look at is pop out. And that basically means an item stands out from many others immediately. In art, they will use the term pop. Something comes out or immediately draws your attention. This is also called pre-attentive processing or tunable detection. Which ones of the red circles in A through F pop out? Certainly A and B. Those red circles pop out. C, it's a little harder to find that circle. D, it takes a bit of a challenge. E, it's possible to find. And F, oh boy, I can still find that, but it's much more challenging. And some things like parallel lines don't support pop out. So human judgments based on relative judgments and not absolute ones. And there's a law called Weber's law that's typically stated as detectable difference in stimulus intensity is a fixed percentage of object magnitude. And that's given as delta I divided by I is equal to K. And basically what this tells us is making judgments without a common scale is difficult. So, which one's bigger, A or B? It's hard with the unframed, unaligned. Framed and aligned, a bit easier to distinguish, but definitely when we have them unframed and aligned, we have a common scale and we can make that judgment. And relative versus absolute judgments are also difficult. Here, A and B, those two squares, are the same color, but you have the shadow interfering with it. In figure A, you can think, okay, well, A and B are definitely different shades of gray, but in fact, B shows that they are the exact same shade of gray. So sometimes difficult for us to make these absolute judgments, and we make relative judgments compared with one another, but even those can sometimes be thrown off. So our abilities with marks and channels are sometimes limited. Anyway, thanks so much for watching today, and we'll see you to discuss this in more detail tomorrow.